Welcome to this video. This is Mark Scythian, FAA licensed aerospace technician, airframe power plant and avionics certified. The date today is February 23rd, 2017. The title of this video lecture is 90mm electric ducted fan percent power setting and propulsion metrics. This is the same identical 90mm electric ducted fan unit as in the previous 4-part video lecture titled 90mm electric ducted fan propulsion mechanics. This lecture is a supplemental data attachment to the original 90mm electric ducted fan propulsion mechanics 4-part lecture. Previously, only the LiPo battery time and use limitations based on 25%, 50%, 75%, and 100% power settings was covered. However, there was no information on calculating static thrust, jet velocity, and mass airflow output propulsion metrics based on 25%, 50%, and 75% power settings. Lithium polymer batteries will provide a constant DC current output when connected to the 60 amp DC brushless electronic speed controller. As the 60 amp DC current remains constant, DC voltage will fluctuate depending on throttle setting to adjust power output to the EDF unit. This lecture will cover changes in static thrust, jet velocity, mass airflow at 75%, 50%, and 25% power throttle settings as DC voltage is varied while 60 amps DC current remains constant. After the aforementioned calculations are demonstrated, 3 propulsion metric graphs will be presented at the end of this lecture. These 3 graphs will quantify the given 90mm EDF propulsion metric calculations. Translating power plant performance calculations and metrics into performance graphs makes operation and field testing far more convenient. Starting out with the original specifications for the previous 90mm electric ducted fan, we have a lithium polymer battery with 5,000 milliamp hour capacity, 50C discharge, and 6 cells. We have a brushless electronic speed controller rated at 60 amps DC. The motor is a 3000 kV DC brushless electric EDF motor. Inlet cross-sectional area 0.068 square feet. Intake cross-sectional area 0.050 square feet. Exhaust cross-sectional area 0.044 square feet. And to go back to the original drawing here, there is your inlet, there's your intake equal to the fan swept area, and then your exhaust nozzle. You then have a fan pitch rated at 3 inches of airflow displacement per revolution, or simply 3 inches of pitch. We already went over the total static thrust, jet velocity, and mass airflow at 100% power in the previous video, 4-part video lecture. So we'll pass through these. If you want to look these over again, feel free to. However, what is pertinent to this video lecture is when we reduce power, how will the jet velocity, mass airflow, and total static thrust change? So at 75% power, we are allowing 75% of the total voltage to reach the motor. So 22.2 volts DC, which is 6 cells times 3.7 volts per cell times 75% power, or 0.75, equals 16.65 volts DC are reaching the motor at a constant 60 amp DC output. 16.65 times 60 amps is 999 watts of DC electrical power flowing through the wire with a 96% electrical efficiency. By the time the electricity reaches the motor, there's 959 watts, which is 999 watts times 0.96 electrical efficiency of DC electrical power flowing through a copper wire less than 10 feet has about a 4% loss of electrical power due to resistance and heat dissipation. So 959 watts DC times an electromotive efficiency of a DC brushless electric motor of 80% equals 767.2 watts of mechanical power transfer from electrical to the fan. 767.2 watts mechanical power at the fan times 80% propeller/fan efficiency results in 613.67 watts of aerodynamic power when at 75% power. divided into 60 amps DC. We have a load voltage of 10.23 volts DC times 3000 kV. So at 75% power, the fan will be rotating at 30,690 RPM. Divided by 60 seconds is 511.5 revolutions per second times 3 inches pitch, or 3 inches of pitch is 3 inches of airflow displacement per revolution of the fan. So if we take that in feet, it's 3/12 feet airflow displacement per revolution times 511.5 revolutions per second. So at the intake duct, there will be 127.88 feet per second airflow velocity when at 75% power. Then we take the intake to inlet pressure ratio of 0.05 square feet divided into 0.068 square feet, and that would be a intake to inlet pressure ratio of 0.735 to 1. So if we want to find out the airflow at the inlet, which has a larger cross-sectional area based off the airflow velocity at the intake, we simply take the airflow velocity at the intake when at 75% power, or 127.88 feet per second airflow velocity through the intake or fan swept area times 0.735. So the inlet will have 94 feet per second of airflow at the inlet. Then we simply calculate the ratio, pressure ratio between the inlet and the exhaust. So we take the cross-sectional area of the inlet, 0.068 square feet, divided into the cross-sectional area of the exhaust, 0.044 square feet. There will be an inlet to exhaust pressure ratio of 1.54 to 1. We then multiply the 94 feet per second airflow velocity at the inlet times 1.54, so there will be a 144.76 feet per second jet velocity when at 75% power. And then to calculate the cubic feet per second airflow at 75% power, we would take the airflow velocity at the inlet, which is 94 feet per second, times the inlet cross-sectional area of 0.068 square feet. So at 75% power, there will be 6.4 cubic feet per second airflow. And as calculated in the previous 4-part lecture, we were operating at 880 feet above sea level and 62 degree Fahrenheit air temperature, which equals an air density of 0.0737 pounds per cubic foot. And then we have 6.4 cubic feet per second, so multiplied out at 75% power, there will be 0.47 pounds per second max airflow. So to calculate the Newtonian aerodynamic thrust force component, we would take the mass airflow in pounds per second of 0.47 and multiply it times the jet velocity of 144.76, that quantity divided into gravitational acceleration on Earth, 32.2 feet per second. So at 75% power, there will be aerodynamic and Newtonian force thrust component of 2.1 pounds of static thrust. Then the fan swept area, of course, is 7.2 square inches as calculated in the previous 4-part lecture. Then all we need to do to find out the cross-sectional area pressure across the fan disc is to take the mass airflow acceleration from the inlet to the intake. This is where the acceleration is happening. The speed itself won't cause the force, but a change in the speed, the acceleration, is where you'll have a sudden change in the pressure above atmospheric pressure across the fan disc. So we simply take the final velocity at the intake and subtract that from the initial velocity at the inlet, but we have to do that in metric values. So 127.88 feet per second at the inlet divided by 3.28 to get meters per second, subtracted from 94 feet per second at the inlet. So 127.88 at the intake and 127.88 feet per second at the intake, 94 feet per second at the inlet. We take the difference in that speed change in metric values. So when we convert and subtract them out, there is a 10.3 meters per second speed change between the airflow entering the inlet as it transitions into the intake. So that happens over 1 second. So acceleration is velocity divided by time, or distance divided by time, again divided by time, or distance divided by time squared. So 10.3 meters per second over 1 second acceleration time equals an acceleration of 10.3 meters per second squared. So then we take the 10.3 meters per second squared acceleration from the inlet to intake mass airflow. We then convert that mass airflow from pounds weight airflow per second into kilograms mass per second mass airflow, represented by m.dot. So 0.47 pounds per second mass airflow divided by 2.2 equals 0.2 kilograms per second mass airflow. And then we just simply use the force is equal mass times acceleration component, and we can calculate 0.2 kilograms times 10.3 meters per second divided into 4.45, the number of newtons to 1 pound, equals 0.46 pounds force distributed across the fan disk area of 7.2 square inches. So when we take the pressure above atmospheric pressure, or the PSI gauge, PSIG calculation, we get 0.46 pounds mass airflow acceleration exerted across a fan disk area of 7.2 square inches. So that would be 0.063 pounds per square inch gauge above atmospheric pressure exerted times 7.2 square inches. So we take 0.063 PSIG times 7.2, so there'll be 0.45 pound static thrust at the fan propeller in the Bernoulli static thrust component. Since high RPM fan is approximately equal to total fan swept area, the pressure above atmospheric pressure exerts evenly across fan swept area. So when we add the Newtonian and Bernoulli thrust components together, 2.1 pound static thrust Newtonian plus 0.45 pounds Bernoulli across the fan swept area, we get a total static thrust of 2.55 pounds when at 75% power. So at 75% power, we have 2.55 pounds total static thrust, 144.76 feet per second jet velocity, and 0.47 pounds per second mass airflow. It's the same process when we calculate at 50% power, except we will multiply the available maximum voltage of 22.2 volts DC times 50%, or 0.5, and start at 11.1 volts DC at 50% power. So when we apply the series of equations and formulas like we did before, same methodology, we have a total static thrust of 1.13 pounds when at 50% power, 96.5 feet per second jet velocity, and 0.31 pounds per second mass airflow. And again, we repeat the process by taking the max available voltage times 25% power, or 0.25. So we'll be entering in 5.55 volts DC into constant current of 60 amps, and then the same series of formulas and equations repeat, but with 5.5 volts as the initial voltage at 25% power, into the final computation through the equations and formulas to result in 0.29 pounds of static thrust at 25% power, with a jet velocity of 48.25 feet per second and a mass airflow of 0.157 pounds per second. So the overview, starting from 0 as a reference point, 0 for everything, and then we increment up 25% power, we get the 0.29 pound static thrust, 50% power, 1.13 pound static thrust, 75%, 2.55 pound static thrust, and 100%, 4.3 pound static thrust. So you can see that the static thrust to power ratio is not exactly linear, but all the other variables pretty much are. So if we graph that in quantification into 3 different graphs, 90mm electric ducted fan performance graphs based off the calculations, we have the top left graph, which represents percent power to static thrust, the top right, which represents percent power to jet velocity, and the bottom left graph represents power to mass airflow graph. So if we look at the first graph here, on the x-axis we have increments of static thrust at 0.5 pounds going up to 5.5, and then on the y-axis we have increments of percentage power in 10% increments going up to 0 from 100. So if we graph all the different points, you can see it's not exactly a linear relationship due to the fact that the square of the velocity is exponential on airflow. But however, if we look at the power to jet velocity graph on the top right, we have relatively a linear progression between power increase and jet velocity, and the same is somewhat true pretty much to the power to pounds per second mass airflow, which the feet per second jet velocity in the x-axis we have in increments of 20 feet per second increments, and the y-axis we have in 10% increments from 0 to 100. Same with the power on the y-axis for the third graph, and then we have 0.1 pounds per second mass airflow increments from 0 to 1.1 on the x-axis. So both jet velocity and mass airflow are relatively linear to power setting, but static thrust is relatively non-linear. As you can see, it's more of a parabolic curve going up. So power to static thrust, non-linear; power to jet velocity, linear; power to mass airflow, linear. So a practical application here would be, let's say we know that there's 4.3 pounds of static thrust total at 100% power. Let's say we wanted half that, 2.15 pounds static thrust. Well, we would look here, 2.15, we need approximately 66% power to reach 50% of the static thrust. So if we trace that 66%, we're looking at approximately 130 feet per second jet velocity and approximately 0.43 pounds per second mass airflow at 50%. So the graph quantification on the thrust component, the static thrust component, is definitely not linear, but once you derive this either through polynomial recalculation, graphic method, or differential equation, you now have a very convenient graph to know where to set your power for a desired thrust component. Other graphs such as aerodynamic drag and lift to drag ratio, those also can be computed and added into graphs, or computational dynamics entered into your autopilots if that feature is available. But it is very convenient to create a graph with all of these different variables taking place, especially if they're non-linear dynamics, like the power to static thrust graph computation here proves. Thanks for watching this video, and have a great day.